So, dear colleagues, the audience, a very warm welcome to our conference on rotational motions, the new observable for seismology. As you probably know, INGV and INFN foster a strong collaboration on research fields of common interest since many years. One of these consists in the research activities at the Gran Sasso laboratory. Besides their ongoing projects between INGV and the Munich group is present today, especially in seismology, and for these reasons, and probably even some more, the idea came up to organize an info day on rotational motions. So why rotational motions? When the ground shakes from earthquakes, from the oceans or the atmosphere, it not only translates up, down, sideways, but also undergoes rotational motions. To fully characterize seismic sources and wave fields, theoreticians have insisted for decades that these motions should also be measured. However, the problems were the substantial technical difficulties in observing rotational motions with the necessary sensitivity. And this is why today the observation of the complete ground motion is still an unsolved problem. As in the 90s, broadband seismometry added a new dimension to the study of the seismic source. Today, more than 20 years later, it is the invention of the rotational sensor that enriches seismology. The classical seismometer measures ground velocity and is sensitive to all wave types, including rotations and tilt. And where I am now? Okay. The rotational sensor is only sensitive to S waves inside the Earth and separates Love and Rayleigh waves at the surface. This leads to interesting applications. For example, volcanoes. At signal periods longer than a few seconds, the whole summit area of the volcano lies in the seismic near field of the volume source, and the displacements are directly proportional to the time-dependent volume displacement of the source. Seismic data contain direct information on the displaced volume, but no information on the size of the source or on the pressure. It's not a trivial task to record long-period seismic displacements on a volcano, since horizontal seismometers do not distinguish between true accelerations of the ground and apparent accelerations resulting from the combination of gravity and tilt. The tilt signal can dominate over the displacement signal at long periods within the passband of a broadband seismometer, and this is the problem. Another application, and there are many applications, the second example is the monitoring of structures, for example. Usually a dense array of seismic sensors is needed to explore all modes of resonance of buildings. With a 6-component sensor, a classical plus a rotational, the number of instruments can be significantly reduced and can see not only bending modes, but also twisted modes on the structure, which might be even more dangerous for the building itself. Roughly 1 year ago, Science published a paper called Lord of the Rings. This paper describes the story of the planning and construction of the first 3-dimensional ring laser called ROMI, for geodetic as well as for seismological measurements. Some months later, in July, I was personally invited to the inauguration ceremony of ROMI in Bavaria and got a first idea why the paper was called Lord of the Rings. However, the inauguration was also attended by researchers of INFN, and most of them are here today. And one of them was Dr. Angela Di Virgilio. And the idea became concrete to organize at INGV an info day on rotational seismology. And this is why we meet today. During the preparation of this event, I recognized that probably there are more than one only Lord of the Rings. And therefore, today I have the honor to present you all the Lords of the Rings. So let me introduce you to the speakers of this morning. We have the great honor to welcome Lord number 1, Professor Dr. Schreiber. Professor Schreiber is a laser physicist, and having completed his studies and PhD at the University of Göttingen in '88, he worked as research scientist at the Technical University of Munich at the research department of satellite geodesy with the focus on satellite and lunar laser ranging, development and application of optical Sanjak interferometers, optical time and frequency distribution. In 1994, he became principal investigator on large ring lasers. And in 1997, he left to the University of Canterbury for a research stay, where he worked on the installation of a quadratic ring laser of saloon dimensions, more or less 3.5 meter side length. And this machine was called G0, and he had the task to study variations in Earth rotation. After his habilitation in 1999, he became adjunct professor of the University of Canterbury in New Zealand, and since 2005, he's appointment professor in Germany. From 2010 to 2012, Professor Schreiber was the manager of the Geodetic Observatory Wetzel and installed the so-called G-ring, a quadratic ring laser with a dimension of 4 meters by 4 meters, based on a monolithic structure. The scientific goal of the G-ring was to study the variation of the Earth's rotation and to improve the sensitivity of the WU-LBI construction. Costs more or less more than 10 million euros, between 10 and 14. So the title of Professor Schreiber's presentation is The Future of Ring Laser Technology for Geophysics and Geodesy. Professor Schreiber recorded with the G-ring also some undesired signals, earthquakes. So he thought, noise for one scientist may be the signal for some other one. And he knocked at the door of Lord of the Ring #2. Professor Heiner Igel, degree in geophysics at the University of Karlsruhe and Edinburgh, PhD at Institut de Physique du Globe à Paris, postdoc at the Institute of Physics, Theoretical Physics at Cambridge, and he is professor of seismology geophysics at the Ludwig-Maximilian University of Munich since 1999. In 2003, the research group of Professor Igel installed a first seismic array near the G-ring of Professor Schreiber, which confirmed the usefulness of the ring laser recordings and confirmed the interest. Igel was fascinated by Schreiber's noise, and they cultivated immediately the idea for the construction of a portable 2.5 meters by 2.5 meters ring laser, which was installed at Pinon-Flet in the US. The final and logical scientific consequence is easy said, it was much more complicated to realize, was a 3D ring laser called ROMI, financed by an ERC grant and realized in 2017. ROMI has a side length of 12 meters and is the first of its kind 6-component seismic observatory based on ring laser technology. This made also Professor Igel become a Lord of the Ring #2. And the fascinating story about ROMI is the subject of his talk called Rotational Motions in Seismology. But the Munich group pointed on a further important goal, the development of portable optical fiber-based rotation sensors for field deployments. And this builds the bridge to the next Lord of the Ring, #3, Dr. Joachim Wassermann. And he obtained his diploma geophysics at Munich, if I remember well, Professor Scherbaum, yeah, and the PhD in the University of Stuttgart with research on Stromboli, and afterwards he was researcher at the University of Potsdam with Scherbaum. And now, since 2004, Dr. Wassermann is the director of the University of Munich Observatory at Fürstenfeldbruck, and they host also the Bavarian Earthquake Monitoring Network. He led and leads many research projects on volcano seismology, array seismology, induced seismicity, developed OBSPI with his group, and works actually in rotational seismology, ROMI, and fiber optic gyroscopes. Together with the French company IXBlue, Dr. Wassermann managed and conducted the development of a first portable rotational sensor, together with the Munich group, together with Professor Igel, and this was called the fiber optic gyroscope and tested in many places all over the world. For example, yesterday in Umbria. His talk is Blue Size, the first portable broadband rotation sensor, characterization and applications. So starting from Professor Schreiber, this was the first part of our presentation ring. So here ends the seismological branch. Now we can go in the other direction. The other way around is the approach, we approach the ring laser from INFN. With the aim to capture gravitational waves, large global observatories were constructed, as, for example, the LIGO, the Large Interferometer Gravitational Wave Observatory. In order to stabilize the LIGO mirrors in Kansas, the removal of tilt was realized by the installation of a ring laser. The Italian contribution to the research in gravitational waves is called Virgo and installed at Cascina, some kilometers east of Pisa. So one of the Italian lords of the rings number 4 is namely Dr. Franco Frasconi. And he's here today. And after his degree in physics at the University of Bologna, with a thesis on the evidence of the beauty quark, Dr. Frasconi worked on particle physics at CERN in Switzerland and DESY in Germany for many years. Afterwards, in 1995, he became research assistant professor at the Syracuse University in the US and was involved in the development, construction, and installation of a Cherenkov detector for particles identification in the study of electron-positron interactions. Since 1997, Dr. Frasconi works at the INFN at Pisa on gravitational waves research at Virgo. One of the most important results, recent important results for the detection of 2 new events by using the advanced Virgo interferometer and breakthrough prize for the discovery of gravitational wave was, he received this prize recently, as also Dr. Angela Di Virgilio. The title of Dr. Frasconi's talk today is Virgo and Seismology. The exploitation of the ring laser technique inside the Gran Sasso lab is one of the major projects of the INFN and mainly followed by the female Lord of Rings, Dr. Angela Virgilio. After her degree and PhD in physics at the University of Pisa, Dr. Virgilio was postdoc and associate researcher at the Purdue University in Indiana from 84 to 86. And since 86, Dr. Di Virgilio is researcher at the INFN Pisa, and since 2002 also first researcher. She was the head of Virgo experiment from 1997 to 2004. And as already said, together with Dr. Frasconi, they received the breakthrough prize for the discovery of gravitational waves. Since 2008, she dived into the world of ring lasers, and until 2011, she was responsible for the G-PISA, the first ring laser in Italy. She was in charge for the development of Gingerino, a 3.6 meter side length ring laser built inside the Gran Sasso Observatory. And this is the smaller 1D version of the future planned 3D ring laser to be installed inside the Gran Sasso, called Gyroscope in General Relativity, or shortly GINGER. GINGER is the name of the project designed to measure the lens theorying effect with a background-based detector based on an array of ring lasers. The lens theorying effect, due to the fact that the Earth is rotating, implies a non-reciprocal effect on the path of 2 beams of light traveling inside a closed path. Dr. Di Virgilio presents a talk about ring laser array for the Gran Sasso. Concerning Gingerino, it was originally planned to have here our colleague Gaetano De Luca, who unfortunately had shortly to refuse the invitation and will today be substituted by Andreino Simonelli, the youngest of the Lord of the Rings we have today here. Dr. Simonelli obtained recently his PhD at the Department of Earth Science at the University of Pisa, and in collaboration with Munich, Professor Igel and Hilda Wassermann, he had a thesis on earthquake-induced rotational ground motions observed by optical rotational sensors. And the title of his talk will be Gran Sasso and Gingerino. And this is the second part of the ring. So the one was Professor Schreiber and seismology, and the second one coming from Virgo, LIGO, and coming back to seismology. And yeah, enough said by myself. We hope you enjoy the idea of our joint workshop. And now I'm pleased to announce the first presentation by Professor Schreiber, the future of ring laser technology for geophysics and geodesy. I recommend to respect the time of 30 minutes. I was a bit quicker, and okay, perfect. Thank you. Welches ist deiner? Okay. Control L, oder?
Yeah. Okay, so this first talk here is essentially technology. So we talk about ring lasers, and I concentrate specifically on the geodetic side of things because I know that Heiner will go to the seismology side of things. So interferometry, optical interferometry, I must say, has gained a lot of interest since the very first interferometers were built. But most recently, when gravitational waves have been detected successfully by a Michelson interferometer. So what I'm presenting here is a different sort of interferometer, which in principle is not really different from a Michelson interferometer. What we have here is a Sanjak interferometer, and basically we have an active interferometer. That means it's a laser. So we have a gain medium, we have a closed enclosed area resonator, we call it a traveling wave resonator, and this has the property that two light beams can propagate in opposite directions. So by means of mode selection through gain starvation, we make it possible that we run this resonator on a single longitudinal mode. And in order to come up with high interference contrast, we use a cavity that has an extremely high Q factor. That means the line width of our laser is extremely small. Okay, now to what is such an interferometer sensitive? It is sensitive to rotations only. And that's because the effective path length of a traveling wave resonator is different from the direction of propagation if the apparatus is rotated. If it's stationary, the two frequencies are the same. But if it only experiences a very slight rotation, then we start to see an interference pattern. All right, so the advantage of such a resonator is that by interfering these beams that are exactly on the same path but not in the same direction, is that many properties of the cavity just disappear as common mode effects. We are subtracting the same effects from both sides. What remains are the effects of the rotational effect that is shown here in this ring laser equation. We have on one side the scale factor, where size and wavelength, where we operate our instrument, are dominant factors. And we do say that the interference pattern here, the beat frequency, is directly proportional to the rate of rotation, including a projection, of course, to the rotational vector. And the thing that we don't like, but what we get for free, is that there are non-reciprocal effects, which are not the common mode effects, which are related to the fact that the laser is running on two different optical frequencies, although only very slightly. These non-reciprocal effects are the ones that cause us the most grief. Okay, an instrument of that size suitable for geodesy requires to resolve Earth rotation to 9 orders of magnitude. And that is a very steep demand. In numbers here, you can say it's approximately 700th of a picoradians per second rotation rate that we have to resolve in order to make it viable for geodesy. Okay, I'm only looking at two most dominant error sources in our gyroscopes, which give rise to this non-reciprocal contribution. And the one is the null shift error here. The null shift error means ideally at 0 rotation, you would like to measure 0. but our instruments usually are very, very slightly biased away from zero. In order to measure absolutely zero, we have to make sure non-reciprocal effects disappear. This is for Heiner here specifically. When you take the non-reciprocal part that is not balanced, then we're down to 19 orders of magnitudes from the optical frequency. But this, of course, doesn't really apply because many reciprocal effects are also there. And okay, second thing here is scale factor error. Normally, a ring laser gyroscope, according to the Sanjak equation, should be unity in the transfer function. Reality is it slightly deviates from this, and most prominently, that is because we have a misalignment between sender components in a 3-component setup, or for a single component ring laser, we do not know the angle relative to the rotation vector well enough. That's on a single sender, that is the dominant issue. I'll come to that. Okay, here is an aerial view of our observatory in Wetzel. We have all the techniques of space geodesy here, that is VLBI, laser ranging, GNSS, of course, and we have gravimetry, and in the far side of the observatory, we have a mount. Underneath the mount is the ring laser gyroscope. Ring laser gyroscopes want to have constant ambient temperature conditions. Therefore, we place them in underground labs. The G-ring laser itself is what we would consider a monolithic structure. It is made from zero-dur. Zero-dur is very low in thermal expansion, and the mirrors here, they span up the area of our gyroscope, and the mirrors are rigidly connected to that structure. And on typical operations these days, we are roughly coming down to 5 × 10⁻⁹. So we are touching the domain where space geodesy can use ring lasers in addition to the VLBI technique. Okay, this is what an interferogram looks like for 2 weeks. These are very recently taken data, and they come from February, and the data set is up to the point where VLBI data is available right now. It's 1 minute averaging, and we see we have something like 40, 50, maybe 30 microhertz in variation here on the interferogram. Small earthquakes look like that. And here in this area, the signal was very quiet. Quiet means no wind that is perturbing our instrument. And here we had a storm over the Atlantic that increases the microseismic background level and comes up as a dithering motion on our ring laser gyroscopes, including friction from wind gusts that hit our mount, and very gently shaking our ring laser. Typically, these contributions here average out when we go to longer time series. Okay, here it's slightly longer. Again, you see earthquakes, and you see differences in the width here of our noise band. Here is when the weather pattern is more of unrest, and here is when it's quieter.
So in the writing, we see the tides there. We see the tides in the previous, right?
Yeah, I come to this. All right, so let's our typical performance as of 2 weeks ago. That's where the data set comes from. If we make an LND, okay, what I've done here is I reduced all the geophysical signals that we know of and I'll introduce them shortly, out of the data set. So it should be, if in the absence of anything that stirs our ring laser, it should be a flat line. But you see, it's not quite that the case. So when we take this up, make an Allen deviation, where we look at delta omega, the variation in the rotation rate over the Earth rate, then we see 1 over square root of t drop off of our signal, as we would expect for a white noise source. As we come close to the period of 1 day, we get a hump like this, and then the data set appears to go further down. This is the last significant data point from the Allen deviation. Okay, what does it tell us here? At around 1 day, we do have residual signals from geophysical processes that's in that hump. And we may also have, it's not quite clear right now, we may also have a very small shift in our sampling relative to the right time. Yeah, so if that clock is slightly out, we have the phase of the reduction is not exactly the same as the nature is. So there may be a small component in it, but I couldn't resolve it up to now. Okay, what do we observe? With a single component gyroscope, we see variations in omega e, that's the rotation rate of the Earth, and we see angular variations of the projection of the instantaneous Earth rotation axis onto the normal vector of our gyroscope. Okay, just to show you where you are, the data set from the previous slides here are average over 1 hour, and we see some residual structure. The origin of that mostly, I suspect that is mostly part of instrumental properties and variations in length of day. That means the term that keeps the Earth rotating either faster or slower. They contribute at the level of 6 microhertz of the Sanjak frequency, and our noise level currently is +5 to ±10 microhertz, I would say. And yeah, so we're close, but not quite there. The signals that we look at is polar motion. In geodesy, that's known as the Opholzer terms. Polar motion has to do with gravitational effects of the moon, and it has therefore a fortnightly period. So these nodes and antinodes are related to the lunar orbit, and it's essentially a pull on the Earth, an extra torque, and the contribution to our measurement signal is about ±20 microhertz. And the period is the sidereal day. The second contributor is about an order of magnitude smaller. That is polar motion effect from ocean tides, and they go with the semi-diurnal frequency of 12 hours, and the zonal tides affect the position of the Earth orientation, and is of the order again of 1 microhertz of plus minus of the Sanjak interferogram. Next one, ocean tides. Again, on the semi-diurnal frequency band, is about even 1 order of magnitude smaller. And I dare to say that these signals are contained in our measurements, but we can't resolve anything near that at this point in time. The advantage of all these signals is they're more or less periodic. These are very periodic. So we know what to look for and we know what the phase is. When you measure something like the lensitering effect, which is a DC contribution, this gives me a lot of cold sweat because it's a DC component and it's an absolute value. Length of day variations, we've seen that before, relative on the smaller section. I think it was that section here. On a longer scale, that's what it looks like, of the order of 6 microhertz. So it's just the domain where we are touching. Again, it has some periodicity, but not in the diurnal band. It's several days. Finally, solid Earth tides. That is a tilt effect from the location where the ring laser is placed. This is roughly half the contribution of what polar motion does to our signal. The polar motion signal was very evident in the first slide of our observations that you've seen. Yeah, ocean loading effects. Ocean loading means the tides at the coast. For us, it's the North Sea coast, and the loading on the coast causes an angular effect on our ring laser gyroscope. Again, it's part of the smallest signal that we can offer in our ring laser, 2 orders of magnitudes down from diurnal polar motion. And a very large term, although with frequencies of, well, I'd rather say periods of 435 days thereabouts. It's a Chandler wobble contribution. That's motion of the rotational axis of about 10 meters in diameter at the pole. And you can see in terms of frequency, the contribution is large. Here, it's larger than an order of magnitude. If you take the full cycle, an order of magnitude larger than the diurnal polar motion. And of course, it's very evident in our ring laser, provided we can have it stable enough for a sufficiently long time. And when we put it all together, all the signals, that is what we have reduced from the data set that I showed you. So this is the combination of all effects over the period of our measurement. Okay, how do we look at things? In order to progress towards DC values, we have to apply corrections to the scale factor. It's not just the geometry that we have to look at. We have a displacement of the beam when it hits the mirror. It's not the front surface that does the reflection. It's a stack of coating layers. So the beam penetrates into the mirror coating and comes out again and slightly displaced. So the area is larger than geometrically it would apply. And that it requires a correction of the order of 10 to the minus 8 relative to the scale factor. The gas in the cavity, the pressure is not 0. It has a few millibars. So we have to take into account a change in the wavelength due to refractive index. Then we get dispersion effects of the mirrors and of the plasma, which are of the order of relative 10 to the minus 7. The wavefront inside the cavity is not flat, it's curved, so we have a Gouy phase correction to apply for that, and that's again of the order of 10 to the minus 8. So these are the very obvious contributors, but the list is not complete. Okay, and just finally, a brief view of the Romy structure. The idea was to make a 3D, three-component sensor, so we capture all the degrees of freedom of rotation, plus add one for redundancy. So we have 4 ring lasers which are operated, and the second guiding theme was all the corners are referenced to each other on a very short distance. In order to make this, well, to prepare the prerequisites of making this a virtually monolithic gyroscope. So we can reference corners here relative to each other to obtain the size and the orientation of the structure and the alignment of the ring lasers relative to each other. Other than these, it's triangular rings, and there's an apex point pointing downwards, and this reference triangular structure sits close to the surface. It's a heterolytic ring. That means in order to run it in the same regime of performance like the G-ring laser, we have to apply stabilization techniques which are known from optics to apply a feedback system that can control the ring laser. In aerial view, we've seen that before. That's the apex point here, 14 meters deep. The ring laser structure is 2 meters below topsoil, and when these enclosures here are put in place, looks like that. And by now it's filled up and it's a grassy surface again. A view from the apex point here, where 3 of the rings come in. So these 2 pipes belong together, and these 2 pipes belong together, and these two, and very close proximity of the corner boxes in the bottom. The currently uncontrolled ring laser gyroscope, because of the thermal extension of the cavity, frequently flips mode. The free spectral range is 8 megahertz from one longitudinal mode to the next. So when thermal expansion pulls the ring laser apart by 1 wavelength, then it hops here. But because backscatter reduces as we upscale the instrument, we do see systematic effects from coupling of the 2 laser beams at a small level. And an active control just makes these things go away, because we're never having a mode jump due to the fact that the size of the cavity is maintained at the same length at all times by a feedback system. And I think that's it, and I conclude right here.
Thank you, Professor Schreiber.
Questions?
Questions?
Julie, in the picture you have shown with the most recent results, you have subtracted all the tides.
Yeah.
Because I don't know if it was clear.
Yeah. That is the raw observation.
Yeah.
And you see that there are several signals that have both the sidereal day length and the semi-diurnal contribution. So when you look at the sine wave here, it appears to be distorted, like you have harmonic content, and that comes from the semi-diurnal part of it. Okay, we have applied to this data set the sum of all corrections here. Yeah? And you see it's also a small slope involved, because over these 3 weeks period, you get a Chandler contribution. From the Chandler contribution, we only see the north-south component because it's a single-axis gyroscope, and that means when it comes towards us or goes away from us, we are close to the 0 meridian, so it's the X component that we see. So having more gyroscopes on different continental plates or vastly different locations, that would be, of course, geodetically very desirable. VLBI is running radio telescopes between 6 and 30 on various parts of the Earth. That means various parts of crustal plate. For gyroscopes, we would require the same thing. The problem is we have a single point of measurement, and we want to extract a global quantity like Earth rotation or Earth orientation from it. And that always has the uncertainty in it. How's the coupling? Yeah, is the gyroscope rigidly attached to the Earth? But what is rigid when the Earth is deformable? Yeah, that means a group of gyroscopes and a combined evaluation of the rotational signal is what I think will lead into the future. You?
But actually, in principle, a three-component gyroscope would be enough to have a unique
Yeah.
So one single gyroscope would be enough to solve.
Yeah. This it's only this thing here. Yeah? If you have one here, then assume Earth is deforming here slightly. That means the motion of the three-component gyroscope here you can capture, but then how much is the location contributing, and with respect to the Earth rotation?
You could use TNS.
Not enough. No, the TNS doesn't resolve it. No. And one of the problems is the diurnal signals and semi-diurnal signals are very difficult to observe with GNSS. It has resonances with the orbit, which are at the semi-diurnal frequency band. It's only VLBI that is, and sensor fusion with VLBI is in discussion as long as we have gyroscopes. But right now, with a single-axis gyroscope, we provide the technology to get to the point it's mature enough to be integrated into a continuous service in VLBI. It's just to outline the difficulty. If you want to know what's the length of day today, you only have to go to predictions. We don't have it. VLBI will take about 2 weeks before we have a measurement. Yeah, so we are always living in the past there, because the measurement process takes time, the evaluation process takes time, and then updating the CO4 series at the IERS also takes time. In a ring laser gyroscope, ideally, you could go into your basement, look at the readout, and say, hey, that's what it is right now. But you get for free what you don't want, all the non-reciprocal contributions, therefore, we're at the threshold, but not there.
So your vision for the future would be to install more?
Yeah, sure. That's what brings us here. Yeah, and that's a point I'd like to make. The collaboration with a suitable sensor here in the Gran Sasso laboratory has large prospects because it's a deep underground facility and not bugged by the wind as we are. And it's more than one sensor, and it's in a different location. So we can study, what is instrumental and what is the location where we place it. And that pushes the way forward. I'm pretty sure we would still find a few subtle things that we're not aware of at this point in time.
Further questions? Andrea?
Besides this large-scale geophysical signal, do you see any disturbance due to sort of problems with variations in the local coupling to the Earth crust? There may be sort of seasonal variations, but these are probably on periods that are too long to affect your measurements.
Yes, we have few effects. Some are related to temperature interaction, and some are interaction that we didn't expect, but we sure get. The deformation with atmospheric pressure changes. Yeah, we've got loading of the atmosphere, and between, let's say, high pressure and extremely low pressure on the storms is an effect of 10 nanoradians in loading, 10 nanoradians tilt coming from dynamic wind patterns. Yeah, that's assume that the low pressure area of a storm passes north of us, we would tilt towards. No, they wouldn't tilt away from it because less load. Stuff like that, we have seen part of it. In other regions, it's not so apparent because fast changes in atmospheric pressure cause temperature variations. It's the adiabatic expansion compression, and temperature effects affect the scale factor. And not so much geometrically, we can compensate that, but temperature also affects the coupling of the laser beams. I didn't talk about laser beam coupling here in the interest of time, but the point is when you run two oscillators very, very close in frequency together, what happens? They lock up, they synchronize. And when there's a little coupling between the two. So we have a Sanjak Interferometer is two oscillators in very close proximity in frequency space. Only for the G-ring laser 300 hertz away. For two optical oscillators, next to nothing. And that means they're pulling each other. And yeah, and this pulling threshold is not constant. It varies with temperature, maybe with mirror separation. Well, not maybe, certainly with mirror separation and all these effects. So we have a small variation in coupling, which is responsible for these kind of signals here. Yeah, it's about a millihertz difference here in the optical beam node. That's because one laser mode has a different coupling than the other. The phase has changed because the frequency has changed, and therefore coupling has changed. Therefore, we get a small systematic contribution. Locking that to a constant state means that we can control the mirror separation to the point that they don't move. That means our standing wave pattern around the cavity is rigid in space.
Okay.
It is almost. That is, it's lots of very, very subtle effects that do cause a bias. And from that point of view, I'm still very concerned that we can measure a rotation rate absolute. Yeah, I mean things with the frequency of a day, we can resolve that nicely because it's periodic and we know the phase. But when it's a DC value, then you have to really nail down every single component that can contribute to an offset, and you must have a complete error budget of that. And it means you also must have the full control. And the full control is somewhat away. But on the other hand, I mean, over the last 25 years that I'm involved in this kind of business, we came down from resolving Earth rotation to approximately 10%, down to, well, approximately 5 times 10 to the minus 9. Yeah, and it needs to be extended for longer periods. Yeah, we can do it for a couple of days, but we cannot do it for a couple of months.
Okay, so I think this is a perfect bridge. No, it's very interesting. So the idea to extend the ring laser in general to other places in the world is the bridge to Angela's talk. the ring laser array in the Gran Sasso. Angela March, I think it's this one.
Okay.
Okay. This is the microphone for streaming.
Okay.
Okay.
Questo? This one?
It's switched on.
Okay. Ah. Okay. So I will just tell you why I was involved in this business of ring laser, and I would outline my view of the array that we would like to build. And I will also say something about Gingerino, which compared to G is a different structure. It's heterolytic, so simple construction, so it's not been proved yet that an heterolytic object can reach the same sensitivity of G. And then at the end, I have some conclusion. INFN is devoted to fundamental physics. I was involved in this business because it was necessary to found a very high sensitivity tilt meter for Virgo. This was more than 10 years ago. But after that, we decided what was necessary to develop this this object independently for Virgo, because and also because for Virgo the solution was found in a simple, much simpler device. After 4 or 5 years for the first development of this technology, we first learned the technology, and then we had the idea that the technology was mature, some sense, to make a test on Earth of general relativity. I mean, lens steering effect is due to the magnetism of the Earth, and it has been already tested at 5% with satellites with different technique. But in principle, with this kind of object, we could make this test on Earth with 1% precision. The beauty of the test on Earth it is that we could discriminate of different theories of gravity which predict the behavior with latitude different on Earth. But anyway, why Uli has shown you some the simple formula that the measured effect, the frequency, is proportional to the ratio area over perimeter, the wavelength of the length, and then we have the Earth rotation rate. But if we make a more careful calculations and we insert all the general relativity prediction, we understand that there are also some extra terms seen by the ring laser, because there is the kinematic term, and then there are these two extra terms, the sitter and lens theory, which are quite large. I mean, there are 8-9 order of magnitude below the Earth rotation rate, and basically they are two rotation, and we see the sum of the three effects. We have published recently this paper which combine all the essential point of the theory. The measurement of rotations depends on the sensitivity you reach. You can use as a lot of applications, essentially for aircraft submarine navigation. We have a small ring laser and fog. If we increase, then we have Givet cell, which is more or less that. But yes, in order to be meaningful for seismic measurement, we have to go down to this sensitivity. Then we have the tides. General relativity is here. Givet cell is more or less there. Our first prototype was GPISA, was around 10 to the minus 9 radian per second. Gingerino is more than a factor 10, 50 better. Atom gyros are around 10 to the minus 9 radian per second. And the tectonic plates are just they demand even more sensitivity, but general relativity. And of course, I mean, we have to be careful what we are talking about, because when we measure a quantity like that, it's always the sum of different effects. So the interpretation of the signal means that we cannot distinguish between fundamental physics and geophysics. We see as a single signal. The main difficulty are that we are looking at signal 9-10 orders of magnitude below the Earth rotation rate, which is always there. And also we have to keep in mind that there are vector in space. There are 3 components. The general relativity test, since it is a DC quantity, requires a very high level of accuracy. But I will not talk about that here. Uli has given you a taste of what means accuracy, because he has shown you all this small detail of related to the mirrors and to how the system is built. But for most of the applications which are not DC, the accuracy is not an issue. Our ring laser is basically composed of 4 mirrors and of a light. The light, as it is a system of equilibrium, and so it has a flat response all over the spectrum, and it gives also a very fast response. I mean, it is depends on how large it is, but we are talking of kilohertz response of this apparatus. So in principle, it is completely flat down to DC. But the mirrors, the relative position of the mirrors plays a crucial role. So more or less, just I can say in a few words that the cut at the low frequency is done by the 4 mirrors. I mean, how you control the mirror and how you make the apparatus. We have this is a gyroscope, and the area versor define the vector in the space, which is your gyroscope. Your answer, it is the frequency, which is the scale factor, which is geometry, pure geometry, and then you have to multiply by the rotation, but the cosine of the angle between the area versor and the angular rotation you are measuring. This is just more, I think, this is a concept, but probably Uli has already expressed you. We have to reconstruct a very high precision of vector in the space using the projectors. 3 or 4 rings are necessary, and it's very important to know the geometry in order to forget about what is going on to the relative position of the 4 mirrors. 3 or 4, I mean, the rings is a ring. When we deal about an array, it's very important to know the relative angle between different rings. Now let's talk just a few words about sensitivity. The sensitivity of an optical system is always limited by the shot noise. This is unavoidable. In practice, in our system, at the end, the shot noise depends on the goodness of the mirror, losses. I mean, the better is the mirror, the lower are the losses, and of the square of the length of the side. Larger is the ring, better is the shot noise limit. At present, we have Gingerino, which is around expressed in radians per second. I mean, in angular velocity, we are at 10 to the minus 10 radians per second over square root of hertz, or G, it is 10 to the minus 13 radians per second in 1 second measurements. We have a confusion with a single ring. We cannot distinguish between angular rotation and the relative angle zeta. So far, we have, I think, well expressed the potentiality for the measurement of rotation itself. But I would like just to say few things about zeta. I mean, this zeta means if we can measure subsidence, local subsidence, or if you can measure a tilt of the Earth rotation rate. I mean, we cannot distinguish between the two, but this instrument can, in principle, provide you a measurement of the angle between the area vector of the ring and the local rotation axis. If I take the general formula, and in order to evaluate the sensitivity, I have to make the derivative of this product respect to the three pieces. I mean, the angle, delta zeta, the geometry, delta S, or the angular rotation rate, delta omega t. I mean, what Uli has expressed you is this part. If we control the geometry, we forget about this part, but with a single ring, we cannot discriminate between this and this. So if we see some changes in practice, could be an angle or could be changing the rotation. Combining more ring laser, it is possible to distinguish between the two. This F1 and F2 are the frequency of two different ring lasers. Gamma is the angle between the two ring lasers, and so this in a 2D model, I can discriminate between the angle and the variation, the omega. So we separate the two. In principle, it is necessary to measure the relative angle between the two rings, and this is what will be done in roaming. And of course, the sensitivity of measurement, the limit in this measurement will pose a constraint in how sensitive you are in one of these two quantities. All of this theory has been published. We have done a big study on all this quantity, and so the scheme, if you like, and this is the paper. Here I have evaluate the sensitivity of this quantity zeta for a short noise limited instrument, considering 1 hour integration time for in function of the size of the square ring, for using the mirrors and the Gingerino one. This is just the mirrors of Gingerino, which are not very good. For G, and considering mirrors 5 times better. I mean, here the scale, we are in, this is 10 to the minus 8 radians. So Gingerino is also, if you enlarge, I mean, the mirrors play a big role. I mean, of course, G is much better because this is the 1 nanoradians. And so in 1 hour, in principle, you could detect a subsidence or a change of rotation axis at this level. This is nanoradians is the green line. Let's talk at the array. I mean, what we have found in our study. I just told you we have published recently that aligning with a special alignment of the different rings, we can avoid the use of the measurement of gamma. I mean, we can. It's not strictly necessary. So we have to align one ring at the maximum signal, put one horizontal, and the third one is not. It must be different from the other two. Has not been decided yet because depends also in the final location. Depends, maybe there is space problem, things like that. But anyway, should be aligned in a plane different from the other two, of course. But it is not necessary that they have to be at 90 degrees. This is a sketch of this apparatus, considering 6 meter square rings. Why do we use, well, in principle, square of triangular are both equivalent. We prefer the square solution because we have developed the method to control the geometry of the apparatus using the diagonals. I mean, in this system, we have the ring, which is the square, and some optical system interrogate the diagonals and keep the diagonals at a fixed length. In this way, it is not necessary to have some extra tools for to keep the geometry, and this with a special alignment using one at the maximum signal, one horizontal. In this case, one is vertical, oriented north. I think north south, something like that, because northeast. In this way, at a certain stand, you do not need any extra tools to control the relative angle gamma. Where we could build this apparatus, at present, this is a sketch of the Gran Sasso. At Gingerino is more or less here. This could be here or inside hole B. There are advantages, disadvantages. In node B, it is close to Gingerino, it is well isolated. I mean, putting doors here, this area is well isolated. But it is narrow. It is not. We could not locate there something vertically because there is not enough room. Or if you like, we should reduce down to 5 meters the side of the square. And there is a lot of water there, so in principle we need a lot of work to eliminate the water. Hole B is very large area, and is almost ready for a new installation. But the isolation from the isolation and impact of the disturbances, I don't know. I mean, this must be investigated. I don't know if some extra area will be available in the near future. This is at present, looks like we could install that there. Let me summarize just in 2 words which kind of sensitivity we could reach with an apparatus between 7 meter and 5 meter side square object, which could be 2 × 10⁻13 radians per second over the root of first, or 4 with 5 meter. But regarding the angle, it is 6 × 10⁻11 radians with 7 meters in 1 hour integration time. These are the limit induced by the shot noise, which is unavoidable. But of course, the real limitation will come in how you build the apparatus. You have to be careful not to introduce other disturbances to the way in which you build the apparatus. This is a different point. We have also to consider that in principle, when you have an effect, some disturbances, in principle with some special study, you can offline subtract the effect of the noise. For the shot noise, you cannot do anything. You have to keep as it is. G is monolithic, has been a tremendous result, but we have to bring the heterolytic one to the same level of sensitivity of G. We are studying the geometry control with our prototype in Pisa. This is GP2, which is a square ring laser with the two diagonals here. Everything is under vacuum. We have already done some exercise of the control of the geometry. This is a highly disturbed place because inside the university, it is 1 hour of in which the geometry has been controlled. We observed 2 or 3 mode jumps. We have to understand why there is this mode jump, but anyway, the control was enough to keep it running continuously. And this is the same GP2, different day, not controlled. I mean, this is free running, and we can see that there are very often breaks in the data, because this is when the apparatus was not working properly. Gingerino has already demonstrated that underground laboratory provides very high thermal stability and quiet environment. I mean, Gingerino is not ginger. I mean, it was built just to see if the location was good enough to install something more important. So from this point of view, has completed its job. And now we leave it running in a continuous basis just to provide data for seismology. It is taking data since May 2017. We have lost a few days for several problems, but it is almost continuous. This is the first set of data, 90 days. We see a few events there. There is also a break because the Gingerino was in split mode. Less than 3% of the data have been removed because we are data with some glitches, some features coming from the laser. We have also applied some filter to remove the backscatter noise. The mirrors of Gingerino are not good, and this has 2 effects. Higher is the seismic shot noise, but also higher is the backscatter noise. But there are ways to eliminate offline the backscatter. We have applied simple filters. We will also make other tests with different kinds of filters. And after the backscattering removal, we obtain something like that. So here I disappeared the days. I don't know why. And I disappear all the. I'm sorry, I don't see that. Anyway, I think it is nanoradians per second, and these are I express as rotation and as tilt, and this is microradians on the other side. The Allen deviation, but okay, is not, of course, as good as G. This is for the raw data. 10 days. Here we do not eliminate any kind of things, just eliminate only with some filter the noise coming from the laser. And we are at the level 1 part in 10 to the 7, 50, 100 times worse than the cell. Conclusion, I mean, the technique of ring laser is mature. I mean, they can run in a continuous basis. Gingerino is almost operative. We have tried to improve. If we have to improve the mirrors, basically. The next step could be to improve the mirrors. And I think I have shown you the potentiality of this kind of object, which can measure rotation and subsidence and at the same time with a very, very high precision. I think. Thank you.
Thank you, Angela. What cost do you estimate for the realization of this?
I think, this is an apparatus that you can always upgrade, of course, especially because in the heterolytic design, you easily can change the mirrors. The mirrors play a big role. I think my estimation, I would be happy to go 1.8 million euros. Something like that. But if we succeed in using the diagonals for the geometry control, and if we can solve the problem of a relative angle with the ad hoc alignment of the different rings, the experiment becomes quite cheap, because we don't need the external metrology, which is necessary to control the geometry and things like that, because the cost of external metrology is very, very high, and I am not sure that it works fine, because it does not take you the position of the spot, but it is more referred to some mirrors, but not to the position of the spot. Since we are talking of nanoradians,
sure.
picoradians, of course, here there are two things to test. First, that we can do with the heterolytic the same thing that Cooley does with the monolithic, and this is one thing. And the second one, it is to align the mirrors. I mean, the alignment of the mirror at the maximum signal has been something which has not been done yet. And we have to see if we can do that.
So cost more or less increases exponentially with sensitivity.
There are these two things. If we solve these two problems, and if the idea of the alignment, relative alignment, not with the head rotation rate works, the cost is rather cheap. Otherwise, I think probably it's I think the external metrology costs more than the ring laser.
Other questions? Yeah.
So the plan is to keep Gingerino operational and in development even when the construction for Ginger will go on?
Hopefully, yes. I mean, we are happy to make it running. We are happy. Of course, we don't take care of analysis of seismic data. I mean, I take care of the preparation of the data. I mean, I have in this paper, which I hope will be soon ready. I mean, this is not the raw data, but in this data I have already done some small. I have eliminated some feature of the laser and eliminating 2 or 3% of the data. This to make your work easier. And also the routine, if you like, we can also apply this kind of routines, which are quite fast. But probably for teleseismic study, I mean, this is enough. We are happy, and I think if we found good mirrors, I would be happy to change the mirrors anyhow. Because the backscatter is because the mirrors are bad. So we will have a much better signal with better mirrors. Not for the short noise, but for the backscatter noise. But anyway, to change the mirror is a matter to have the system off for 2 weeks.
Fine. Other questions? Okay, that's not the case. Thank you, Angela. So we directly shift to the next talk. Gaetano Luca is not here, but the talk about Gran Sasso and Gingerino will be by Andrino Simonelli. And it should be this one. This is the, yeah. Okay.
So good morning to everybody. I'm proud to be here to present the results of the operation and the construction of Gingerino ring laser inside the Gran Sasso that has covered the period of part of the period of my PhD studies. So you already know where Gingerino is located, but I will go a little bit more on details about the construction and the sensitivity, especially with an eye for the seismological study and interpretation of the data. So a brief summary. I present the instrument first, then I will provide you a basic simple formula for interpretation of the data in the setup that we have for Gingerino ring laser. And then we follow the story of the observation and the scientific publication that has been done with the data provided by the instrument. So we start with the observation at teleseismic distances that occurred first. from the period when we committed the instrument. And then a particular eye on the 2016 Central Italy seismic sequence that all of you know very well here. And we will summarize with the conclusion and the future project and developments for this instrument. So let's start from the first zone. So Angela told you that Gingerino has an heterolytic structure. So what does it mean? It means that there is a central pier made of granite with 4 arms that are hollow inside. So there is a particular engineering study to keep it light. As you can see from the cut drawing, it's inside it's empty, so it looks bulky, but it's lighter than what you could expect. This is the location inside the knot beak of the Gran Sasso laboratory, where in previous time was installed the Crescentini strain meter. So what are the problems and the benefits of an underground installation? First, the thermal stability. The thermal stability is very good because of, and it's a passive stability. What is not so good is the forced ventilation that is needed to remove the radon that is naturally emitted by rocks from the cavity, and this somehow affects the long period of the seismometers. But a very easy cure for this problem can be, for example, to put like a pressure doors, as it's standard for every high-end seismic observatory. So after some months of hard work on this instrument, we came to the final design. So now you all know how a ring laser made. So we have 4 mirrors in 4 corners, and we have a seismometer in the center of the ring laser that is provided by the ENGV, and is the station called GIGS that is on the ADA database. This is a more technical scheme on how we detect the signal by combining the 2 counter-rotating beams with a photodiode, and we also keep monitor of the single intensities of the 2 beams, because these observable are required for a second post-processing of the data that allow to reduce the backscattering induced noise. And these are the observable that are object of my studies, our studies. We have what we call a 4C, 4-component station. So 1 component for vertical rotation rate, 3 components are the 3 components of ground displacement or acceleration or velocity provided by the seismometer. So here we see the sensitivity of the instrument, and we can see that from 1 Hertz to 100 of seconds, the sensitivity is below 10 to the minus 9, much more below. So we go up to, let's say, 10 to the minus 10 radians per second. Of course, this number, if you're not familiar with rotational seismology, are not so useful now, but if you in the next slide, you will understand what does it mean. So let's check what is the basic theory that we use for that we use since decades to analyze the rotational motion in 4C components. So suppose that you have a log that is traveling in the north direction, causing a displacement in the east direction. Then from theory, you can extract this very simple equation that states that these observations, so the vertical rotation rate, the rotation around this axis, is expected to be in phase with the transverse acceleration, that is, by chancing this scale is on the east axis, and it's scaled by 2 times the phase velocity of logarithm. So with this simple scheme, by using a grid search over the azimuths, thus optimizing the coherence between the 2 signals, you can identify the direction of the incoming wave field. But at the same time, in a bandpass approach of the signal, you can estimate dispersion curve if the seismic phase that you are observing is dispersive. So, and that's the case of the log width. So we, after a few months, after I think it's after one month of operation, we had an earthquake that was generated by the mid-ocean ridge. It was a magnitude 7, 5 kilometer deep. And this was the first detection of an underground rotational signal. That's why I'm stressing out this, because there were already attempts to install ring laser underground. So Angela spoke to you about GPISA. GPISA was smaller, was only 1.6 meter inside. And there were earthquakes occurring. The seismometer was showing data, but no data from the rotational sensor. So that's remained like a mystery for a while. But then when we moved to a larger ring laser with higher sensitivity, well, you can see that the red trace show a nice signal from the earthquake. So you see like the peak arrival. These are units are radians per second, so this is 10 to the minus 9. If you think about the sensitivity plot, it's like 10 times over the noise limit. And you see the onset of the log waves. And if you try to compare with the zero-lag correlation, after rotating the trace toward the theoretical decadence, you see that the coherence between the two signals rise up to 1. And this is a validation step that allows us to, for example, to estimate the back azimuth that is coherent with the expected one, the theoretical one, as well as a phase velocity dispersion curve that is consistent with the continental prim model for a 35 kilometer thick continental crust. So this was the first detection that was published in a paper in Annals of Geophysics. Of course, as you already know, we are not alone in the world and in Europe. So actually, right now, there are operative 3 ring lasers in the world. On this side, we see the single component, so the one that are sensitive to this rotation rate. We spoke to you about DRXL, that is providing a very important and consistent data since many years. And it's somehow the reference for all the improvement that we do in the ring laser technology, especially for the long-term stability that is it's outstanding. This is our instrument. It's located in a different, of course, a different region, in a very seismically active region with a complex tectonic and with a complex geographical setup. So we expect to see some differences in the signals, because what we do are local measurements, and somehow the imprint of the local structure should be evident from the data. Then in the second part of my PhD studies, I had the honor to take part in the construction of the largest system in the world, that is a 4-component ring laser that is able to reconstruct with an unprecedented sensitivity the ground rotation vector. And we are starting to collect the first data from seismic images. So these 3 ring lasers provided some months ago. I think it was at the same time of the inauguration of the ROMI ring laser. And in this plot, I show you the vertical rotation rate from ROMI. So it's not all the 3 components, because we want to compare with other ring lasers, so GVXL and Ginger. And what is evident, for example, you may ask, why do we see rotational signal in the P coda? This is what we usually explain with a local near to the receiver conversion of P to SH waves, that they also lead to a transverse kind of motion, so that generates rotation. And this kind of conversion seems to be more evident in Bransasso. This is I mean, a 3D effect, so it looks like the signature of the site is present. So now we let's say move to shorter distances, and we go to analyze sequence of the data that we recorded with the ring laser during the 2016 seismic sequence. And in particular, I want to focus on the 26th of October. That is a famous day, unfortunately, because it's the day when occurred the famous Rizzo earthquake. So the third main shock of this very important sequence. That was there was like a magnitude 5.4 before, and many other aftershocks. And I show you this plot because I want to show you the consistency of the observation of the injury. So this is a continuous. Angela said we are including 95% of duty cycle, and here you can easily see how stable are the observation during half a day. And in particular, the instrument is not perturbed by these strong motions, because one question is the sensitivity. Also, another question is the dynamic range, because we want to cover also strong rotation rates. So with the data we collected with this sequence, we were able to prepare a manuscript that is recently reviewed by DJI. So we selected only 33 events because we have to say that we had some timing problems with the two different digitizers, because the signal are digitized by two different apparatus. So and it's really mandatory to have a hard constraint on the time. So these are the events where we are 100% sure that the timing is correct. So these 33 events, they range from the magnitude 2.9, 5.9, 5.4 to the 3.5 over a span of I think it's 1 month, and I think central distance that ranges from like 30 to 100 kilometers. So here you see again where is the location of the instrument. It is inside this small gallery. It is inside the Grassasso, inside the context of central Italy. And in this plot, you see again in the color code that we like. It's the red usually represents the vertical rotation rate or rotation rate in general, and this is the transverse acceleration, so already rotated toward the theoretical mechanism. These data offers us the first chance to process a sequence and a group of events, and so there was need to develop some statistical processing technique in order to since the data set is growing up, so we need to summarize somehow the results in some symbolic plots. So first study was the study of the direction of propagation of the LG phase. And in this plot, we show what we estimated for the real event from the 4 component events, and we compare with the theoretical mechanism derived by the station to receive. So you see that the data, they look quite, the trend is similar to the theoretical one, but if we do a statistical analysis of the misfit between the expected and the measured, we see that in a polar plot, we have, after modeling the distribution with a Gaussian kernel density estimator, we find a systematic misfit of 10 degrees that we can explain with a structural effect, as well as a possible seismometer misorientation that can be measured and fixed by, for example, using a portable fiber optic gyroscope, just using it as a north finder. Because in the Grassasso there are many metallic structures, so they can bias actually the measure that you do with a compass. And this was presented to the GTS here. So then the second catch that you can achieve with such a station is a phase velocity estimation. So in order to produce this analysis, we report the amplitude spectral density of rotation rate in red. So rotation rate has units of radians per second, and black vertical acceleration has units of meters per second square. So in this plot, we are comparing two different observables, but I want to, I did it with the purpose to show you that the difference in orders of magnitude is somehow the order is 3 orders of magnitude, that is meters per second, so that's already a phase velocity. So the processing is to take the ratio of individual spectra relative to different phases. So for example, T-coda phases, S-coda phases, and G phases. Every ratio then is averaged over the entire data set, and these produce a final plot that is the phase velocity estimation for the 3 seismic phases, where only but it is not really long, it's LG, but this is the only one that show a normal dispersion as expected. And these are the estimations for the P and SH. One thing that I want to stress out is that, for example, here you see a peak. The blue line is the noise level prior to the earthquake. So it looks like there is a resonance that is excited by the earthquake, and it's only present in the ring laser. So that's why we decided to limit our analysis to 5 seconds, because we really think this is an instrumental effect. And if you take the ratio, then that can lead to false estimation or biased by something that is not connected to geophysics. And another approach that was published by Eagle, for example, for analyzing telesymes with the G-ring laser data, is a bandpass approach where you simply compare and rescale the bandpass version of the seismogram. And for graphical reason here, you don't see the coherence, but for example, it's pretty evident if you take like 5 seconds, 6 and 7, and the ratio of the envelopes of these bandpass seismograms gives a number that is reported here. That is again the phase velocity for each dominant period. So these are Gingerino, in summary, it's able to record almost every 7 magnitude 7 earthquake occurring in the planet, and of course, given the unique location, is also able to detect very local high frequency events that are of course interesting because we can explore near source effect, non-planar waveform propagation, and or everything that involves, for example, the complexity of the structure given the geological setup. So we have another. Gingerino is actually the largest ring laser in Italy, and the other one is in Pisa, but it's not devoted to seismology. The sensitivity is pretty high, 10 to the minus 10 radians per second. And now you know why I stressed 10 to the minus 10, because if you just scale by the expected phase velocity for every model, then you can retrieve what can be the ground motion that you can measure with the seismometer. The duty cycle is extremely high, and this is due to the thermal stability that keeps the optical cavity frozen. That's what we want as a final result for a perfect ring laser. But not only that, but that's the first good step. So we observed the seismic event, and as I said already, the location is very important because we can study near sources. And in 3 years, we produced more than 5 scientific contributions with this instrument. And the next step would be to have a more consistent study of phase velocity versus azimuth, possibly highlighting anisotropy. And we also would like to finally see the ocean-generated noise in the rotational component. So in the next week, there will be an installation of a new set of mirrors that will be possibly will increase the sensitivity in order to achieve the same comparable sensitivity of G, let's say, at least in the seismic band, because the mirrors are like like tires for a Formula 1 car. So if you have good tires, then you can go very fast. And we would like to have good mirrors to be very sensitive, especially in the part of the spectrum that is dominated by the shot noise. So that's all. Thank you very much.
Well, thank you, Antonino. Some questions, Heiner?
Did you check the this funny frequency pattern that you observe in the noise as well? Before or after the earthquake?
Yeah.
Just see during the earthquake.
Yeah, it's in. So this again, this blue line is the noise level of Gingerino before the earthquake, and you can see that the line is present.
I see.
And it's excited by the earthquake. So it looks like maybe a structural resonance of the instrument. If you don't see it in the seismometer, it means that it's. I mean, it's not related because it cannot exist a rotation without a translation, at least in some simple models of the medium.
But it's not actually not so simple, because if you have a seismometer which is attached to, say, exactly right, the seismometer is right on the structure.
In the pier, yeah.
So if the pier is resonating somehow, you should also see it. So it's actually a resonance which is pretty unfortunate.
No, I think it's intended modulation of the delivery cavity because of vibrations in the GameCube.
Yeah,
We have never seen such things in foreign. You see, the important thing on the optical interferometer is the flat spectrum. Yeah, and it's an artifact from the construction.
But even so, if it's in the mechanical construction, you will see any translation motion on a seismometer, which is much more sensitive to this vibration. So you should see it also in the seismometer. It's either a construction which is only acting on the optical system or distortion.
well, and the noise can be injected in any phase. For example, it can be a combining noise. The ringers are a very complex instrument, and we didn't explore completely the all noise sources. One is backscattering, and it's been mentioned before. But I prefer to keep it simple and just see how to process the data. Of course, it's surprising because up to now, a seismometer is still more sensitive than the state of the art.
And then what's the temperature stability numbers? The big variation or variation over an hour or something like that?
I think it's a fraction of degree over days. Do you have a number, Nicola, for example?
100 millikelvin 10?
No, 10, not 10. No, 100. It's 1/10 of degrees.
10th of a degree.
But unfortunately, our probes are not working. We refer to all the measurements. We will replace the probes as possible. Well, first you said that we will replace the mirrors, but we don't know. Yeah, because we are testing new mirrors, and if we are happy about the new mirrors, we will replace the mirrors.
And we will be happy about the data.
Every time we touch Gingerino, we may make some. We are never sure that we can start it. Say like that.
Yeah.
Regarding this resonance, can you please show the Gingerino setup? Right. The Gingerino setup is different from the others because the pipes is not very rigidly attached to the monument.
And it was our decision to try to avoid any contact between the pipes and the external world. This means, but the pipes itself can rotate, of course, and probably the 8 Hertz is due to that. This is something that can be improved if necessary. There is also the fact that the discharge is not rigidly attached because also the discharge is suspended. We will see. I mean, I don't think we have much time to work on Vigilino, but if necessary, we can make it tighter. But probably is not something such a big deal that is interesting.
Do you expect an influence of the tunnel geometry on the signals? Because I remember some experiment in the BFO, in the Black Forest Observatory, putting the seismometers in different locations near the wall and the center, and this made some.
You mean like a pipe? I mean a guided wave.
Yeah.
Yeah, that's something can be simulated, for example. But now the question is if the pressure variation on the tunnel they are causing a real ground motion, so it's something you cannot feel with the pressure type, or so if it's something, or it's just a coupling, so a flow that is passing through the instrument and those tilting, and that can be healed by the doors. Because actually we don't, I don't show in my presentation, but the noise level for the micro size part of the seismometer is pretty close to the low noise model. So it means that the site is quiet. Then we have this drift for long periods, let's say over 20 seconds, and this drift has a trend like 1/f noise, and the 1/f noise is usually generated by turbulence or phenomena that are related to quasi-similar processes like turbulences. So in my mind, I hope that this can be fixed in an easy way. Otherwise, we have to maybe model the tunnel and Grand and see if there are some eigenmodes that we can be excited by the seismic solutions.
Okay, so we are perfectly in time. Dr. Vasconi, I think it's the next talk. Virgo in Seismology is the title. Yes. Okay. Okay.
Okay, thank you very much. This is your glasses?
No, not mine.
Somebody forgot glasses. Okay, anyway. Okay, thank you very much for inviting me to this workshop. I changed a little bit the theme of the workshop because I do not talk about seismology and so on, but I would prefer to talk about the technique we are using to protect our suspended mirrors from seismic noise in the tentative to detect gravitational waves with advanced interferometer, which is a very large Michelson interferometer with two fabric cavity along the two arms, 3 kilometers long each one. First of all, let me spend a few words about seismic noise, because this noise is one of the limiting factors in the sensitivity of ground-based interferometers for gravitational waves detection. And in particular, this noise limits the sensitivity of our detectors in the low frequency region. When I say, when I talk about low frequency, I intend starting from 20 Hertz going down towards 1 Hertz. And this is the most important reason for which in all the experimental area, in all experimental sites all over the world, a very precise monitoring of the local disturbances as well as of the standard seismic activity is performed and deeply studied. And in particular, this study is very important to improve the duty cycle of our interferometers. So let me recall for a while very stupid information, but extremely important for us. So this is, I reported in this slide, a very famous campaign of measurement performed by Peterson and co-workers, just to mention that this is a sort of our reference plot to compare the seismicity all over the site on advanced Virgo, LIGO site, but also all over the world. And in particular, from this set of measurements, we can infer the upper limit and the lower limit from seismic point of view. And we use these two red scarves as a comparison every day in our working life. So let me stress again that seismic noise is a tremendous impact on our experimental apparatus, in particular for what concerns the microseismic activity. And this microseismic activity is very important in the frequency region below 1 Hertz. And as you know better than me, that this kind of microseismic activity depends on the oceanic and large-scale meteorological conditions. And this particular component of seismic noise is extremely important for the duty cycle of our experimental apparatus. In the region around 1 Hertz, this kind of seismic noise is due to the, of course, local effect, while for the frequency above 1 Hertz, there are many natural sources and many additional sources that can be related to the standard human activity. But let me show for a while, as I said a few seconds ago, the typical seismic curves of our sites. Here I reported on left side the seismicity of our seismic profile, let's say, of the Virgo area, together with the other detectors all around the world, and particularly the 2 LIGO detectors and the Geo600 detectors and so on. Of course, also in this plot, you see the famous Peterson curves, the lower limit and the upper limit. On the right side, you see the seismicity of our LIGO Virgo site, typical LIGO Virgo site. The first plot, the first panel on the right side is along the west arm, and in particular, the blue curves represent the seismic motion in a high seismic level condition, while the green curves represent the low seismic condition, which we prefer to use to work in this working condition, just because in this case we do not have many troubles with our feedback control system. So just to give an overview of the sensor accommodated all along the interferometer arms and the central building, we have so many seismometers all around the site, together with some specific sensor attached on our super attenuator. The super attenuator is the mechanical structure ground connected designed to suspend and to isolate from seismic activity, seismic noise, the optical elements of our advanced Virgo interferometer. And here on the right side, you can see the effect, the wind effect on the displacement of the super attenuator suspension point as measured by our local sensor. LVDT means linear variable differential transducer, which is a sort of displacement sensor installed on top of the suspension system. I'm going to show you something about our experimental apparatus in a moment. Here, the red curve is a low wind action on our suspension point of each super attenuator, while the black curves represent the impact of the wind during a particular bad days, bad weather conditions. You see, the difference is very important because the displacement of the suspension point range from a few fraction of micron up, a few micron on top of the suspension system. But let me stress again why we need to suspend, or if you want, to isolate from seismic noise our free-falling mass. So the main goal of our activity is, of course, the detection of gravitational waves. But just to give you an idea, the main goal of our interferometer is the measurement, the measurement of the differential distance between two mirrors along an arm, which is of the order of which is 3 kilometers, and comparing with this distance, with the length of this arm, with the typical amplitude of a gravitational wave signal, which is of the order of 10 to the minus 21, 10 to the minus 22. This means that we need to control in a perfect way the position of our mirrors. And this is an important issue to have included in the experimental apparatus, a well mechanical. We decide to use a mechanical system to isolate from seismic noise the free-falling mass, the mirrors. Seismic noise, as I said, gives the most important contribution in the low-frequency region. This is another important information, because another important goal in our activity is to detect, to observe gravitational waves signal coming out from binary neutron stars or whatever it is, as long as possible in our experimental apparatus. This means that it is extremely important to extend the detection bandwidth in the low frequency region. Low frequency means a few hertz, possibly down to 100 millihertz or better. This is the main idea. And this is the reason, because since the very beginning, more than 20 years ago, we start to study a specific equipment to be used within the Virgo interferometer before until 2011, and now with advanced Virgo interferometer, just to isolate in a proper way from seismic noise the optical component. So, just to give you an overview of the working principle of our super attenuator, as I said to you, the super attenuator is this mechanical system adopted to isolate the optical component of our interferometer. Here you see, here is the optical component, is the mirror. The size of this mirror is 350 millimeter. The total weight of the mirror is just 42 kilograms, but the total weight of this last stage, which are used to call it payload, is about 300 kilograms. And the total length of this suspension chain is of the order of 9.5 meters. So along this suspension, we have these three legs mechanical structure working on the working principle of an inverted pendulum. And within this three legs mechanical structure, we have six or three seismic filters composing the multi-stage pendulum of our chain. And finally, we have the last stage of payload, and as I said, is the most important element of our suspension system. Again, seismic noise is the most critical point for the sensitivity of our ground-based interferometer. The typical seismic noise in the Virgo site at 10 Hz is of the order of 10 to the minus meter per square root of Hertz, many orders of magnitudes above the target noise level. And this is the reason because at a certain moment we decide to use as an isolation system a mechanical system based on the multi-stage pendulum working principle. Of course, if you use a simple multi-stage pendulum, you can guarantee a good isolation from seismic noise in 2 degrees of freedom, typically the X and Y degrees of freedom, but you need also to have the same performance in vertical position. And this is the reason because we decide to include in our simple pendulum the elastic element to suppress also seismic noise in vertical direction. Finally, just to give you again an overview of all experimental apparatus, we have in total 10 super attenuators, 7 long super attenuators, and 3 short super attenuators 4.5 meters high. And our system is an hybrid system. This means that during the development of this mechanical structure, we conceived the mechanical structure in such a way to confine all the mechanical mode, the inner mode of the structure in the low frequency region below a few hertz, 4 or 3 hertz. While in the upper part, above 4 hertz, we use the passive performance of a multi-stage mechanical pendulum. Here you can see the performance of our super attenuator at 10 hertz compared with the standard seismic noise level in our Virgo site. So this is the idea. Above 4 hertz, we use the passive attenuation performance of a natural behavior of a multi-stage pendulum, while in the low frequency region, we perform an active control with a specific electronics and sensor. Again, let me give you some additional information about our interferometer. On the right side, you see the optical layout of the advanced Virgo interferometer. Here we have the laser source. At the moment, we can reach more than 100 watt in power sent in this direction. This is the 3-kilometer arm along the north direction, while here is the west direction 3-kilometer arm. Of course, in this schema, you can imagine that each optical component is suspended by using this super attenuator. And the reason, as I said, is the isolation of this optical component from seismic noise. Just a few pictures to better show you the super attenuator. You see, this is a long super attenuator with a multi-stage pendulum chain in the middle. And you see also the 3 structure leg, the inverted pendulum structure leg. And this is a bottom view of the top stage. And here you see the triangular blades as an elastic element to obtain the same performance, the same attenuation performance in vertical direction too. And here some picture of the seismic filter. And here is the top stage where many sensor and actuators are accommodated, and spend a few words in a moment about these tools. And here you see a general view inside the central building where the core business of all our experiment is accommodated. Here is the beam splitter, here is the north end tower, the signal recycling tower, west input, sorry, west input and north input, of course, and all around. Okay, I anticipated a few words about the reason because we need to make an intervention in the low frequency region with an active system in our super attenuator. The super attenuator, as I told you, has been considered as confining all the resonant modes of the mechanical structure in the low frequency region. At the very beginning, this low frequency was set at around 5 Hertz, but in the going on with our activities, we moved in the low frequency region, and at the moment, this cutoff frequency is around 3 Hertz. So all the inner mode of the mechanical structure are confined between 40 millihertz and 2 Hertz, and in this region we have an important swinging of the mirror, and this is the reason because we need to perform a very active mode damping and a hierarchical control to better control the mirror position. Let me spend a few words about the hierarchical feedback control implemented along the chain in 3 different points at the very top of the suspension chain, where we control the tidal of the suspension point and any kind of drift of any origin of the suspension point, together with the active mode damping of the super attenuator normal mode for seismic noise depression, while the second intervention in the hierarchical control is done at this level, where we have the last stage of the suspension chain called filter 7 for historical reason, and we have also another mechanical element, the marionette, which is used to orientate in a proper way the position of the mirror. At this level, the second feedback control point, we perform an active pre-damping at the level of the filter 7 as a back reaction of the effect when feedback control is engaged at the level of the payload, and in particular at the level of the marionette, and we control the Z displacement and angular displacement of the mirror. Finally, during the lock acquisition of the interferometer, we perform a third point. We perform a third action as a local damping of the mirror, applying a viscous damping to lock the interferometer in a final position, working in a proper way. Let me spend a few words about the top stage. Here is reported a sketch of our top stage, where, as I told you, we have three LVDT sensors. LVDT sensors are displacement sensor to monitor the position of the suspension point of the multi-stage pendulum chain. And together on LVDT sensor, we have also accelerometer on top of this guy. And we have a coil magnet pair as an actuation system, which is used in our feedback. At the very beginning, just to control the tidal motion of our suspension point and to suppress the normal mode, to reduce the normal mode vibration at this level, we use the information coming out from the displacement sensor, the LVDT sensor, the red cards in this scheme, together with the inertial information coming out from the pre-accelerometer. Everything is blended together through the use of DSP technology and sent to the digital to analog converter to send back a feedback action at the level of the coil magnet pair. All this stuff has been developed by our group, by our INFN group, and this technology uses a very new DSP technology, and in particular, all these three guys have been included in a single board, all all embedded in a single board, and this new electronics is another novelty of the advanced Virgo setting up. So again, just to give additional information about the setting up, here is the top stage of our super attenuator, where we have a vertical accelerometer, horizontal accelerometer to monitor the motion of the suspension point, the inverted pendulum legs, the three legs mechanical structure, and here we have some the actuation point used for feedback purpose. So here I report in these two plots the tidal monitoring during the last O2 run, when we detected the first signal of gravitational waves. Here is the tidal monitoring along the two arms, the north and the north arm is the red curve, while the blue curve is the west arm. Here is the monitoring over the entire period of O2 run. This means we have, I'm plotting here the behavior of our suspension over the 25 days of data acquisition system. While in the second plot, the right side, we compare a typical tidal effect along the typical differential tidal effect in our super attenuator with a standard model of tidal motion. Okay, but this is just a part of our problem. Another important and crucial, more crucial problem is the Newtonian noise, which is originate from continuous motion of the Earth crust, driven by the tidal stress, seismic motion, and the mass density fluctuation in the atmosphere. This Newtonian noise gives an important contribution in the region below 10 Hertz. But the one crucial point is that Newtonian noise typically decreases in underground sites, but we have to take also into account this source of noise for the present interferometer, because fluctuation of gravitational noise field induced by seismic noise is directly coupled to the test mass, to the mirror, and this creates a sort of short circuit with the attenuation structure. And so this is extremely important for the present detector, but also for the near future detector, because Newtonian noise represents the most critical sensitivity limit in the low frequency region, just for the third generation of interferometric detectors. Here in this plot, I reported that the present sensitivity curve of the advanced Virgo detector and the sensitivity curve for the Einstein telescope observatory with two different configurations. And as you can clearly see, there is a very important contribution from Newtonian noise. And if we intend to go on with our study on gravitational waves, it is extremely important to reduce, to bypass, let's say, the problem of Newtonian noise. And this is the reason, because we started to investigate on the possibility to reduce Newtonian noise on the present apparatus and in the future apparatus. So at the moment, we have just a couple of hypotheses in the mitigation of Newtonian noise. Of course, the first one is represented by the possibility to select an underground site where we put third generation detectors, because the surface wave seismic noise is exponentially reduced with the depth, and this is a good method to isolate in a proper way our optical component. But there is also another possibility to subtract Newtonian noise using some correlated response of an array of displacement sensor, which can be subtracted. This Newtonian noise can be subtracted from some relevant stationarity quantity continuously monitored. And here I report a very simple expression to subtract Newtonian noise. And this is what we are doing for the future activity around gravitational observatory. Here I compare the seismic activity of the present Virgo site with the seismicity of the another underground site, the green curve, which represent the seismic noise level in the Cagra interferometer in the under construction at the moment. They plan to put in operation the 3-kilometer long underground interferometer in the second half of 2019, join the collaboration, the network, the international network, together with Advanced Big and Advanced LIGO. While on the right side, I'm reporting some site selection for third-generation gravitational waves detectors seismicity, and you can see here that there is a very good site in Italy, the Sosenatos mine in Sardinia, which represents the best site in Europe to host the Einstein Telescope Observatory. This is a very strong candidature. Just to spend a few words about activity in progress on the Newtonian noise subtraction. Just recently, 3 weeks ago, we installed a set of seismometer, 36 seismometer, inside the West End building at the Virgo site, and here you see the spectra of each seismometer installed on the ground floor on the West building. This has been done just to implement a technique to subtract Newtonian noise. The study has just started, and here you see the behavior of the response of this seismometer, because in our building we have two different concrete soil attached in correspondence with the tower, and the other soil, the external, let's say external soil, which is not connected to the central part of the building. So you see that the most important vibrations are very close to the building wall. So a very preliminary tentative to find a correlation between two adjacent seismometer inside the West End building is reported in these three scatter plots for three different frequency, 10 Hertz, 15 Hertz, and 20 Hertz. Again, this is very preliminary results. I got this information just yesterday morning, so this is really a very, very preliminary. So the idea is that to go on with all this activity, because we plan to select pretty soon a site for a third generation gravitational wave detection, which is driven by the possibility to mitigate seismic and Newtonian noise, getting some important improvement below 10 Hertz. Sosenatos mine seems to be a very good candidate to host the Einstein telescope, and in the meanwhile we try to make a continuous monitoring on seismic noise and Newtonian noise for future development, in particular for a new version of super attenuator and studying the Newtonian noise subtraction as a fundamental tool aimed to important improvement on detectors' sensitivity in the low frequency region. Okay, thank you very much for your attention.
Really impressive how many efforts you
Yeah, absolutely.
to improve the signal quality.
Yes, this is extremely important for the present situation, but as I try to summarize also for the future generation detectors, because the idea is to build up a huge area where install a very large interferometer with arm 10 kilometers long each one. But it is also clear that we need to improve also our capability to isolate from this kind of noise source our optical elements.
Questions?
The Brownian motion noise on mirror coatings. What is the latest on that?
Oh, this is another crucial point in our investigation, of course, and this is the reason because in the first generation detector we use a small mirror. This means that the dimension of the mirror is identical to the present was 350 millimeter, but the total weight is a double. The first generation detector used 20 kilograms mirror. Now we are 42 kilograms mirror, just to overcome the problem of, let's say, thermal noise due to the mass of the mirror, due to the Brownian motion of the surface of the mirror, and also there is a huge effort in improving the quality of the multi-layer coating to be attached on the surface of the mirror, because this is an hot point in our investigation study, because we need to acquire important new technology to overcome this kind of noise source, which is extremely relevant in the same, roughly speaking, in the same frequency band, the low frequency band.
So I would say to continue because we are quite in time.
Okay, thank you.
Okay, thank you. Professor Igel, about Romy. Is this one? Okay.
Okay, maybe let me step back for a moment again. We're talking about rotational ground motions, and we had 100 years of seismic instrumentation. We've learned a lot about the Earth's interior, seismic tomography. We've learned a lot about earthquakes without measuring rotation. So that's why I think the question, why the hell should we record that? And is it really useful? Is a good one. But the previous speaker has actually made clear that to fully understand weak motions, small motions, we really have to maybe think again. And it's important to note we have never measured the complete ground motion, because the complete ground motion, as we've understood today, is not only translation, it also is a rotation. If you want to actually continue a measurement point in its trajectory, we have to measure all 6 components. That's very important. Another important point that has not been highlighted maybe strong enough today is every seismometer is sensitive to rotations. So you will also have a combination that you cannot, you basically cannot distinguish the two. That's extremely important. So that's kind of the background, what we have been interested in this topic over the last almost 2 decades now. So I want to make even a more general point about where we are in terms of seismic instrumentation. I think we had in the last 10, 20 years, maybe 2 revolutions. One was basically computational seismology. We're now capable of simulating 3D structures and so forth, and understand the Earth's interior much better. The other one has been the use of seismic noise. And I forecast that there will really be a major step happening in the next maybe 5 to 10 years, and that's in observing ground motions. And I see this as an axis from starting from a single point measurement to billions of sensors. That's not my wording. At the AGU, actually, people started talking about billions of sensors. We are clearly operating on the left side here, trying to actually understand the single point measurement, what really is capable to be measured at a single point, much better with ROMI, with portable sensors. But there's also a lot of things happening at the other front, you know, having observations, let's say, with smartphones, or that's in emerging technology, distributed acoustic sensing. So I think in the future we will have much more heterogeneous sensing of ground motions, and actually we don't know what to do, how to combine these things, and there are many, many open questions. So we're currently trying to push forward just simply the science of measuring ground rotations, which is not trivial, and it's still not really solved. So in that sense, I do think it has been mentioned before, it still is an unsolved problem. The sensors, that was the starting point maybe a few years ago for field studies, and this is what seismologists need. You know, ring laser is nice and well, but that's for observatories. You know, seismologists need portable sensors they can put in the field and measure, and we need many of them. They only start to be available. I mentioned this before. There's the ambiguity of ground motions in seismometers. That might not be so important for our standard daily procedure of monitoring earthquakes, but for you it's very important. Long period seismology, free oscillations on volcanoes is actually extremely important. And as that part of the main objective of my talk, there's actually a lot of interest in, there's a lot of potential if you have 6 components. And the main message is, if you observe 6 degrees of freedom or 6 components, your point measurement allows you to extract information similar to having a small array. And it's obvious where this is useful. It's useful when you do not have the option for many, many stations. And that can be a borehole, it can be the ocean, it can be a planet. And that's, I think, where many of these applications are interesting. So important to note that what we measure is the rotation. It's actually the curl of the wave field. It's a vector wave field that we're measuring. These are, let's say, the classic vector component of ground velocity that we measure. And at the Earth's surface, actually, because of the free surface boundary condition, 2 of those terms vanish, and you only actually measure the changes of the vertical component of motion. But this means, basically, in principle, and that has been kind of a critical point, you could also put a seismometer array into the field and use finite differences to get these gradients or the rotation components. And we've done that in 2006. It was published a couple of years ago around our ring laser in Wetzel. So this may work very well, but it doesn't work well in general. And there are also problems with this. For example, if one of those sensors is not very well coupled, you're taking differences between amplitudes. It's like a numerical calculation. You will the accuracy will depend on the size of the network compared to the frequency band. So this does not take the necessity to try to be able to measure the rotation or the gradient directly at a single point. And that's basically what motivates us to push forward that technology. So we've seen some data from the Wetzel ring laser, which is basically has been the best over the last 10 years. And I invite you to look at this database. And we actually record automatically now these motions, and these graphs are automatically generated every day when there is an earthquake. I'll show you, of course, a classic example. That's the Hoku-Okui earthquake. And what you then get is, for example, this is a transverse acceleration measured at a point and the rotation rate. And if you superimpose it, you almost don't see the difference there. They have the same waveform, and the information, of course, is contained in the amplitude ratio, which allows you to extract phase velocities. And these are, of course, then very powerful observations to, for example, I'm not going to spend much time. This is an estimation of back azimuth that it actually allows you also to separate out love waves. The correlation coefficient is basically almost 1 in the long time window containing the love waves, and that actually allows you to also now with 4 component or 6 component to eliminate P waves, S waves, Rayleigh waves using these kind of information. Dispersion was mentioned. The power, of course. Imagine you are on a planet with 1 station. This will happen this year with the InSight mission. Unfortunately, not really with the 6 component sensing yet. You can extract. You see this dispersion curve, the behavior of the phase velocity is a function of frequency, and you can use that basically then to derive such a dispersion curve with some errors and come up with a one-dimensional velocity model. This is actually analysis of 1 single earthquake and a local tomography, which discovers the fact that the Earth has a crust, which is well known. But if you're on a planet, that might be useful information that you can extract simply with a single point. So another example that has not been illustrated before is, again, this is a Tohoku Oki earthquake, a long time window. And what we look at here is in red, this is a sliding time window. We look at the correlation as a function of propagation direction. So we rotate the horizontal components, and we basically ask in which direction is the correlation maximum. And interestingly here, you see before the earthquake, there seems to be these are love waves. Love waves coming always from basically the same direction. So why is that? This is ocean-generated noise. These are love waves that come from the oceans. Then there is the earthquake, and it's like a flag. You point in the direction of the earthquake, and it goes back to the noise. You can then again extract phase velocities. And that's very interesting because you can, the ring laser is a polarization filter and actually only measures love waves. And that allows you to do interesting science with that. And that's, we've seen this before. Actually, you showed this. This is the, over the year, the amplitude behavior of the G ring. So you can see in winter, this is summer, this is winter. In winter, you have a lot more rotation noise. And that's, of course, because in winter we have the big storms in the Atlantic, which is the dominant factor of our ocean-generated noise. You see the same in the vertical component of a standard broadband seismometer, and these type of observations allows us to characterize the ocean-generated noise, both with the ring laser and with the standard seismometers, and to understand the origin of the noise sources, because that's not very well understood. Nobody understands at the moment why there is so much energy in love waves, because the oceans, there's a hammer on the seafloor that should generate primarily Rayleigh waves, but we observe a lot of love waves. That's the ratio that's recently published, a couple of papers by our collaborator Toshiro Tanimoto, working with us. And that's why this wow is here in red. It's surprising that sometimes even love waves are more energetic than Rayleigh waves, and that nobody has a really good explanation for this at the moment. So there's also some interesting science. Now, in the very long period, long period range broadband seismology, if you have large earthquakes, these are surface waves that go several times around the Earth. Again, in red, the ring laser, in black, the seismometer recording. You can nicely see the correlation and anti-correlation of the waveforms, exactly the same. It's simply mathematically the e to the ik minus omega t or plus omega t that leads to this behavior. And if you look at these seismic waveforms, you can also think if you add those up, well, then this would vanish. If you just subtract them, then these ones would vanish. It's like a way of separating wave field directions, in one going up, going up. in that case, left or right going, or east or north going directions. And you can do the same for upgoing and downgoing wave fields, which is a work that was published actually just a few weeks ago by the Zurich group. So also here, there's interesting observations to be made with this spin laser technology. These are the free oscillations now. These are amplitude spectra, and I will not spend much time on this, but these are complementary observations of ground motions. And I just like this illustration. If you put yourself in here, for example, you would basically, for that particular mode, primarily measure an amplitude in the rotational motions. And if you put a sensor here, your rotation sensor would have very little information, at least for the vertical component, and the translation sensor in this direction would have maximum information. So in terms of applications that are possible, and that's one of the reasons why this is such a fun topic, there's actually quite many. And I just want to highlight a couple of these applications, and Joachim will speak about some of them later. But let me categorize again where these rotational measurements might be useful. One is actually to get more accurate ground displacement recordings. And that's particularly interesting for OBS measurements. We're starting a collaboration with La Spezia, NGV connection here, because it's very well known that all the horizontal components are very, very noisy on the seafloor, and it's because of tilt coupling. That has been postulated for many, many years, but nobody has ever measured it. We've had the first measurement, and briefly will show that. On volcanoes, it's important, and the long period band is important, and I believe also for applications like gravitational wave detections. Now, there's a lot of interest if you have sparse networks. I mentioned this before, particularly on planets. On seismic source inversion, there's of interest, and also earthquake engineering, and Joachim will show some examples here. Now, OBS, I think, is one of the most immediate applications. If you look at, we've seen this before, a noise level of sensor here this is in the sensor in the Indian Ocean, is actually extremely noisy at very long periods. Now we're entering the realm where we would like to look at waveforms. And so we want to have accurate data in this context. So what we've done, we've actually put a relatively low resolution off-the-shelf rotation sensor on one of those systems and put it in the North Sea. And these are the observations over 70 hours or so. Again, this is now a horizontal component of an OBS seismometer, and that's the corresponding rotation motion. So if the sensor does this would be a horizontal rotation, so a tilt component. And what you can see even by the eyes, they're highly correlated. In particular, now this is a coherency plot in the frequency band around 10 seconds period. There's a very, very high correlation. At the end, there's a storm. It's the average correlation is 0.94. And the conclusion is, yes, actually the OBS measures primarily tilt on the horizontal components, so you can throw the data away. Now, of course, you can plug this into the seismometer equation and correct through it. And so that's the goal, to basically build a 6-component OBS prototype that can correct for this automatically. Now, I will not spend much time. You can do tomography with this new observable as a ratio between acceleration and rotation. It's interesting because some of you know sensitivity kernels. The sensitivities, of course, you expect that local where you measure, make your measurements, and that's in particular useful, for example, for planetary applications or also for other applications. We posed the question, how does it help having 6 components for seismic source inversion? That's a standard procedure you want to do in an earthquake service, like here in Italy. Normally, you want to determine point source characteristic, the location and moment tensor components, or for larger sources, rupture velocity, rise time, and static slip. I will make a long story short, but we pose the questions in a way like this. Let's assume we have, let's say here, 20 standard 3-component seismometers, and we replace them by 10 6-component seismometers. That would be a fair comparison, because then you have the same kind of number of traces, and we solve the inverse problem in a probabilistic way and look into the resolving power concerning earthquake source parameters. And again, I'm making a long story short. The message is here, and these plots are showing actually a Shannon information gain for many different scenarios. One with a classic 3-component stations, one with half the number of 6-component stations. So each point in one of those graphs is an inversion for example, a moment tensor component or source depth. The message is here, actually almost always we recover the source properties better with half the number of stations with 6 components. Now that's a theoretical result, there's still open questions, but that indicates actually similar to the situation the oil industry is interested in, that when you measure the gradient as well at a point, you can actually halve the number of sensors that you use to obtain the same information about the wave field. So in terms of recent developments, of course, there's the multi-component ring laser that you've heard before, and I'm not going to say much about this, except that we're now producing the first data, which of course we find very, very exciting. Thanks to Uli, we are, in terms of sensitivity concerning seismic observations, already basically where you are with the G-ring. Correct me if I'm wrong. That's the recent message. And so this has been done before. This is the vertical component, containing love waves here. That's new. Now this is the horizontal motion for the first time at a similar resolution than we had before with the G-ring. After properly rotating the components into the same directions, we see an extremely stable correlation here of the back azimuth, and of course the fun should now start in trying to interpret these kind of observations. A very new development is, and that's a paper that's come out a couple of weeks ago by the Zurich group, and we have high hopes. This is a kind of an automated procedure now to calculate, to process 6-component data and come out with something like this. This would be the back azimuth and incidence angle, if I'm not mistaken, of a phase in a certain time window. In that case, would be the P wave. And so this would be imagined to be able to do this time dependent along your wave field. It's like similar to a classic array analysis. And that would be fantastic if that would work well on these kind of 6-component data. So this is where we're going. Now, Joachim will spend some time on this, but we have been very, very excited that almost exactly 2 years ago, IXFlu, this company, accepted after we went there and brought the case forward to open a new product line for a portable broadband seismic sensor, because that does not exist, because we need broadband. And so this is now existing. We provided the specifications. It was last year HU for the first time presented at a conference, and we're now starting measuring with this, and some of the first measurements have been undertaken actually in the Colfiorito aftershock region and Stromboli. So Italy plays an important role in that story, and seeing something like this now, a 6-component measurement here, you can say with quite similar signal to noise ratio. So 3 components, up, down, x, y, or northeast, and 3 components of rotations on the same axis, is really something we can now start using for our science. And again, frequency-dependent correlations. But this is only starting now. So the message is here. This is now really something that's taking off, and it's an invitation, also maybe in collaboration to help us in the next maybe 1 to 2 years. It will be decided whether that's useful seismology or it's just an interesting scientific application. And we're totally open. But I think now there's some very interesting science to do with these new observations. I should mention, as said before, it makes a lot of sense to make these such observations on planets, and we've submitted a proposal to Horizon 2020 just a few days ago for developing a 6-component sensor for space. There are experiments will be going on in Greenland in summer, supported by NASA, with this sensing system, with a view to seeing maybe if one visits rocky, icy planets, this might also be a very useful concept. So with this, I was very fast and slowly. I should want to conclude, leave this conclusions up. Most of this I've said before. I do think there's a lot of potential applications with this 60-degree of freedom concept. In the next years, we'll show we need to demonstrate that this works with real data. I should also mention, for those interested, there's since more than 10 years ago, an interest group in international rotational seismology with lots of literature and things, data access, and there's another meeting planned next year in Taiwan. And with this, I would like to stop.
It was not me. It was not me.
Yeah, that was the indicator that my talk is now over.
Yeah, it was precise. Any question?
A question for you and perhaps also the other one. We had an application once where we use very high noise sensors together to reduce the noise.
Yes.
Roughly like 1 over square root of n. Have you ever tried to combine all these, bring laser gyro together, between 2 in Germany?
Yeah, that's a very good point. That's a classic textbook application that you add some sensors and you noise. At the moment, so far, we basically have had 1 sensor at best. We did have 2 sensors or maybe 3 sensors even, but actually of very different kind, very different sensitivity. But we're looking forward to having, let's say, 3 of these blue side sensors at one point to understand also its noise characteristics. So it's a valid question. But of course, at first we would like to have this the sensors.
By the way, we also manufacture fiber optic gyros.
Okay, great.
Have you observed the near field data with the portable sensors? What's the dynamic range? Are they expected to work also in near field?
We have the Cotirito experiment here, which is kind of close. It's not so far away. 30 kilometers there.
It's not strictly speaking a landfill application.
There is a paper came out with this R1 sensor, which is the liquid-based sensor, which is probably not very good for waveforms. But the amplitude range they recorded up to, I think, 10 to the -4 radians per second. So we're already starting to be in the range of kind of degrees per second. So to the top there can be very high rotation rates. For some telesizing, we're talking 10, for example, cushion generated noise, we're talking 10 to the -12, 10 to the -11 radians per second. Very small, but it goes up to almost 10 to the -4, so we are 7 orders of magnitude. The good thing is that you will know that it's relatively easy to observe high rotation rates because that's where the technology comes from. every airplane, every rocket, every has small gyroscope. So that's not the problem. It does mean also that you could possibly use such a sensor for both strong motion and weak motion. Do you agree?
Yeah, and not yet. So, the dynamic range of the fog is very high, and you can extend it infinite.
One point maybe the cost. And so,
well, yeah, blue size at the moment is around 40,000. But this is, basically still includes the our R&D, research and development as costs. But of course, that can come down. And also, if it takes off, there might be developments in kind of slightly different technological directions. So, but this was our. We said it cannot be more expensive than the high-end broadband, classic broadband seismology that we have achieved.
Is there interest in exploration in geophysics?
There is a strong interest in exploration has been for a long time. Of course, exploration at the moment is basically on the floor. There has been a very strong interest for one reason, and that's if you measure a wave field that's like with 100 by 100 sensors, if you measure the gradient as well, you can beat Nyquist by a factor of 2. And that means in each direction you can halve the number. So if you have 10,000 sensors, you would have only a quarter of those. And that's much less logistics, and logistics is money, and for them that's the biggest issue. Schlumberger has probably patented the hell out of this already, but there is interest. But at the moment, of course, all the research labs in the oil industry have been gone.
Further questions? If not, we invite Joachim for the last talk.
I promise to keep it short. Even the title went shorter than proposed.
Yeah. NGV 60. 60. Yeah. Okay.
So you've heard a lot of gyroscopes which are, let's say, more or less static, so they do not move. And my talk will be focusing on portable 6C sensors. What is the application for those? Again, a motivation. What are the 6C benefits? For instance, you could do wave field radiometry without an array, actually, or let's say half of the station or a quarter of the station. You could then produce some sort of surface waves maps in different frequencies. So that means tomography. There would be a so-called possible easier solution for the Helmholtz equation. I do not go in this detail, which is more or less array-derived things. I think a very strong field of application is the estimation of local velocity profiles with one sensor only. This is the most important thing for me in application. It's microsonation. Microsonation could be done by H/V. That's a single station technique, but it's not reliable. We have no idea about, sometimes it works, sometimes not, so it's a bit unreliable. The standard techniques means you do, let's say, spatial interpolation functions using a couple of sensors. And this is very hard to maintain, of course, in a city. So I took not now here the normal figure from Los Angeles Basin, but this is here Canada, Ottawa. That means you can do profiling and estimating the velocity profiles, so the impulse response of the soil structure below a certain point by just measuring with one signal sensor, and then you walk through the city. That's a major improvement for me, at least. Another topic which I already mentioned is the dynamic tilt correction, which is normally not so important for classical seismologists. As soon as you go closer to the source, or you move to a very vulnerable, let's say, structure like a volcano, which is deforming a lot during explosions, you would face dynamic tilt. So it's not static tilt, but dynamic tilt.
And here is a theoretical example shown with different components of the seismometer, and you see here in red to black a tilt contamination of the signal of the seismometer, which is then, of course, is mapped into a moment tensor inversion result. So we start from this is the input, and what you get out is here 80% DC, it's still a strong DC coupling or DC result, and 20% then isotropic part. So you would mistaken this as an opening fracture, while it's still a normal double couple. This dynamic tilt is, well, it's very important for seismometers when you act already in the downgoing slope from the transfer function. Another point, which is also volcano related, as also mentioned already, it's reducing the non-uniqueness of moment tensor inversion. Bean and others from Ireland, they showed that the result of a moment tensor inversion is pretty reliant on the first, let's say, 100 meter of shallow velocity structure at a volcano. That's mainly I'm referring to. So that means this is the true source. It's a pipe. If you ignore the shallow velocity structure, it will lie flat. That's completely wrong. The geometry is wrong. Then, as you see here, there's the hope that was shown parts of it of Bernauer and Stephanie Donner's paper recently published. You see here the difference between a pipe or a crack pipe or a crack or pipe model is very small, because we only look at the translation motions. There might be, or that's the hope, that using 6C sensors with the rotational motion included, you would be able to resolve this ambiguity here with different mechanisms. So the question is, do we have these portable sensors? And we think, at least in Munich, we think that this principle of interferometric fiber optic gyros is the right way to go for having portable sensors. Because they are existing, they have some really good advantages. So that's nothing else than a Sanjak Interferometer again. So we have two counter beams in the coil, in a fiber coil. And what you measure here is not frequencies as the laser interferometer you have seen so far, but it's phase shifts. Pretty simple. So what you see here is a change of the light brightness. And this change in light brightness is more or less nothing else than a time difference. So no moving parts, that's good. So there is no transfer function, it's flat, that's very good. It's absolutely not sensitive to translation in motion as long as the fiber coil is not deforming, something important. And with the closed loop sensor, that's answering your question, in principle, we have a huge dynamic range. It's from degrees per second down to, let's say, nanorods per second, in principle. Physically, it's not possible because the more sensitive sensors are huge, they're big. And to use that in slow motion, I would say that's not really feasible at the moment. There are also cons. Because we have a closed loop sensor, this closed loop sensor actually introduces higher noise. While let's say the biggest problem with the fiber optic gyros, we have a rather high power consumption at the moment, at least, present technology. So I mean, this is general. So you produce also these kind of fiber optic gyros, I would guess. The thing we had in mind is reducing the power. Well, this is not really reducing the power. It's at 24 volts. That's actually, no, is the 60 watts is still a high number for seismological applications. If you have no power line at hand. At that version, it was still 24 volts. Meanwhile, we have 12 volts application or 12 volt model. We have GPS, PPS, synchronized timestamping. This sensor was built already with a mini-seed output, so it's a seismological data format. That's good for us. And we have a TCP protocol to ask for the data. So it's not a seedling server, but it's close to it. So we grab these data out of these sensor as it would be a digital a normal digital seismograph. The design has changed now tremendously. That was a prototype of it, measuring at Giotto in Florence. I show some results later on. That's a very nice thing too. Of course, you can also use this gyro for orientate your instruments to north, which is a bit expensive actually for just doing it north way. Okay, stealth noise. I mean, fiber optic gyros are not the only technology existing. What you see here is a comparison between different fiber optic gyros. So in colors, it's the blue size 3A. That's again a PSE. You have seen it. That's the most familiar thing for seismologists. Geodesists or laser physicists always argue with Allen deviation, which is most of the geophysicists do not know what it is. So I prefer to do this PSD plot. What's very nice is that the stealth noise is more or less flat here in this band, and we are almost there where we want to be here. So it's 1 nanorod per second per square root hertz. A very good sensor actually in the higher frequency range is this called ATA sensor, which is a magnetohydrodynamic sensor. I have no clue how it works physically, but it's pretty good. Let's say 1 hertz and above, but it gets wild when it's going to longer periods. So it's a huge sensor. It would be nice to have it small, and then it would be perfectly fitting the need of exploration seismics. But it's also pretty large, the whole thing. A comparison to existing fiber optic gyros, let's say from the industry, that's a LITAF sensor, which is worse, of course. It was not trimmed for having these weak motion possibilities. And this one here is the already mentioned R1 liquid-based sensor, which is not bad by itself, but the problem is it's a liquid-based sensor. There's a diffusion equation in there, and so it's temperature dependent. That's not good for us. So it changed its behavior with the temperature, pretty strong. Okay, what next? The applications. So the first thing, I pretend to be a volcano seismologist always, because it's cool to be one. And the other thing is, it was exactly the idea moving this sensor together with a trillium compact close to the source. So being in the near field where the tilt effect should be strongest. That was the idea. Unfortunately, always when I visit Stromboli, and Thomas know this, Stromboli is cheesy. There's no activity or very low activity. So that was sort of a failure, but in any case, you see here there's a base plate, rigid, and on this base plate, we install the 3-component translational motion and the 3-component rotational motion. And we had actually 3 instruments with us. So one we placed here, one here, one there. That's just a single component vertical rotational motion sensor. And try to see what we can tell about the local velocity structure. That was the first idea, you know. If you know the heterogeneities of the local structure, you can estimate them, and then you can remove it out of your signal forever. So you know it exactly for that side. And that's nice, of course. Okay, how to do this? We use, well, that's the signal, sorry. So that's the first 6-component recording at the volcano, as Stromboli. These are explosions, and that's a local earthquake. And what we first are interested in is not the explosions, but the noise, the volcanic tremor in between, to see what we can tell about the local velocity structure. And the technique we do, it's just a short figure about the self noise of the instrument. In blue, it's the recording of ground motion in acceleration. So it's ground acceleration, and in black, you see the recording of the rotational rate of the corresponding component. And what's surprising, or what for me first surprising, that the rotational rate is so high frequent domain. So it's a lot of energy coming in high frequency. after thinking a bit more, it was clear actually, here you scale with the velocity, with the local velocity. So going higher means looking shallower, and shallower means slower. And then this translates in larger amplitudes in the rotational motions. That's what we do now here. I keep it completely simple. So always I assume plane wave. That's the simplest assumption I can do. This equation you have already seen. So that's rotational rate vertical. That's transverse acceleration. And this scales by 2 times the phase velocity of SH or log waves. I cannot distinguish between them for now. And the same is true for the rotation for the radial wave. So this scales the transverse acceleration, rotation rate scales with the vertical acceleration by the radial wave. So very simple. And if you look closer to this, there is no cross correlation needed because this already is a linear equation. So what you can do is just linear regression in both directions. That means orthogonal distance regression. So there is no need for doing a grid search, but you can do just simply, you perform a scatter plot, which is shown here. So in blue it's rotation rate, in green it's acceleration. You produce a scatter plot and then try to estimate the slope. And the slope will be exactly the phase velocity or 2 times the phase velocity. That's it. That's easy. The only thing what you should do then, you should also rotate accordingly your seismometers or the rotational motion. So for each frequency now, we estimate this for each time window I'm sliding over the tremor sequences. I estimate the amplitude ratio, and this gives you an estimate of the phase velocity. And this is nothing else than counting how often a certain phase velocity is taken. And you can estimate a Gaussian kernel, so density kernel estimate. You have the mode, and this is your frequency. This is the velocity for that frequency. The width is your error, and this you transport then to your inversion. And that's done here. So for each frequency, you create these kind of plots. That means you estimate a phase velocity here for this frequency, and then you estimate, you shift your frequency bins a bit further up, and you get your dispersion curves. This you can do now for log and radial waves because we have 6 components of measurements. What you also can do additionally is using the old standard H/V technique, of course. Should also apply this kind of things. And at the end, what's coming out is these kind of velocity inversions. So it's a 1D inversion using D-inver from Vatelet, the GeoPsy software. I'm sure you know this. And I found it rather striking that, I did some experiments before with also active sources. I know also Jürgen Neuberg was doing active sources, those experiments, sledgehammer experiments, and there's a very low velocity layer at the top, let's say around 600 meters per second for P. Then it jumps a bit higher to 800 meters per second, and then at 80 meter steps, it jumps to, let's say, around 3,000 meters per second. And of course, the same behavior you can also see for the S wave. If you compare this to known velocity models, of course, it's at least in the range. I do not say it's exactly what we get. We can also see in other experiments, but here for this model, it's rather crude. So you would not see the first layer here, the first shallow layer, so you would ignore it. And that means you would do wrong when you do the moment tensor inversion. That's exactly the point. Okay, that's for this one. A very strong application. Important is it's a plane wave assumption. So it fails, the velocity estimate might completely wrong, because if this is curvature in there, it's closer, the velocity would be probably higher than what I estimate because of the wrong assumption with the plane wave. What I did here, I tried to omit, of course, the explosions. I throw them out because there I'm pretty sure there are a lot of body waves in there. Because we have explosions, whatever. So I just took the background noise, volcanic tremor. Even so, remember it's a polarizer. The only thing what I see is H waves, nothing else. There's no P wave, no SV wave, no nothing. It's just SH waves. And that's already surprising that you have so many SH contributions at a volcano, which is more or less, you know, it's an explosion. That's sounds strange. Whatsoever, even if the plane wave assumption is failing, the direction of the incident wave field is still correct because we are measuring at a point. That would be different with an array application. There, also the azimuth is wrong, possibly. That's shown here. So again, the setup and doing a beam steering backwards, you will see here, you know, that's the crater region here. And that's the noise wave field is pointing exactly to the crater region, which is nothing else than volcanic tremor, of course. It would be expected. What's not expected that it's H waves meaning. Okay, now the next application, it's microtonation in the city. So that's also paying off, I think. So we did some measurement here right in the middle of the city because the local supplier, energy supplier, they want to drill till 2030, 18 boreholes, deep geothermal boreholes right in the city limit, which causes some concern about seismicity, of course. And what we want to do, we want to model the response of the channel structure beforehand in order to say, well, you're not allowed to produce an earthquake larger than 2, for instance. That could damage them. So we did a 6C measurement here, 1 hour measurement, same technique, and that's the result, actually. And what is very nice in this case, I do have geological information about the underground. So you see here several steps in velocity. So it's P and S again. And the first step is exactly the pre-water table from the first water layer. Second step is the water layer Munich is shrinking out. So that's the tertiary water layer. And then the question is what's deeper down? So I have no information with using the CC technique because there is not much contribution of low frequency energy coming from the city. What I can do is, of course, then include H over V, and I would also detect a lower layer in this case. Whether this is true or not, that's to be confirmed because the drilling was not deep enough. And finally, technical, we have already seen, Giotto tower, different levels, different storages here. We put one sensor one night here, and we moved it in the morning down here because we had only one sensor present at that moment. You see also, it's a new hobby of mine. I'm collecting strange parking permits. So I was allowed to park right in the front of the church of the Basilica. It failed actually in Arezzo. There I got a ticket. It was not very cheap, to be honest. Okay, anyway. So what we measured here is shown here at the top. That's the top spectra. Again, PSD versus frequency. And that's actually the vertical rotation component. So that's the twisted road of Giotto. It's doing this. That was to be expected, actually. What was strange here is this peak, because this scales with the fundamental mode in north-south or east-west direction. So doing this. So first of all, my idea was, because I was talking to colleagues from Florence, it's a rocking mode. So you do this, so it's jumping around. You can produce, of course, rotational motion by doing this. That would be strange somehow, that the whole tower, the Bell's tower, is jumping around. I think a bit more than it was clear. If the motion is like this one, you have, of course, rotational signal also in the upper floor, in the frequency range where you have the normal modes, the fundamental modes of the tower. And that was then also proved when measuring down here. The signal became fundamentally smaller. It was much smaller. That was then clear. It's this movement. Well, then we finally, of course, had something which would be also nice to see. Near-field effects of local seismicity, and that was a measurement we have done together with Thomas. Andrea was with us also close to Colfereto, and that was because here we have the aftershock sequences. Of course, it would be nice to move even closer, but at that time, sequence was still ongoing. There was a lot of damage, so we decided not to go there, not to, let's say, put more pressure on the local authorities to give us the permits and so forth. And that's basically it. And I hope you have seen that there are a lot of applications using portable sensors, and we are close actually to get a reasonable good one. That's not the only one, but it's reasonably good already. Thank you.
Thank you, Joachim. Yeah, some of these results I know.
Yes, of course.
So, some questions. I think the applications are manifold, possible applications. Some questions. Oh, you're too hungry?
Too tired.
Too tired. Yeah, the problem is the cost, yeah, as we already mentioned before. So it should be, in order to lower the cost, it should be important to start, yeah, to buy some more instruments.
I mean, I'm not selling the instrument for the company, but of course they will choose the whole product line if there's not enough interest from the seismology. That's one thing, and of course this kind of closed loop sensor is not what we actually need. Our dynamic range is pretty limited. So for the strong motion case, that would be also sufficient to have a more, let's say, classical fiber optic gyros. For the weak motion, we need more sensitivity and less self-noise. And there might be in the future an open loop temperature compensated fiber optic gyro, but this is, of course, first of all, we have to prove that there's need in seismology.
My question.
Yeah.
Is it possible to measure? I'm not an expert of it. Is it possible to measure the density profile of the crust with such techniques?
Well, always just in connection to velocity. I mean, it would be nice to have a direct connection to velocity, to density. That would be really nice, but at the moment, of course, it's just the gradient of the wave field, so it's just again the velocity. Unfortunately, the big advantage, it's the velocity, or it's an advantage and a disadvantage. It's the velocity very local. So you have a really focused knowledge of your velocity structure right under your sensor. That's something which is normally not known in seismology.
Fine. Good. So we continue now in the afternoon with a meeting, a roundtable discussion about future projects and so on. And therefore, to participate in this meeting, we have already prepared lunch outside, and so I would propose to go to lunch now, and so we are together, and afterwards you can move to a smaller room and start the discussion. Okay. Thank you.